of gravitational field theory, our topic that we looked at in 8.2, to develop the concept of gravitational potential energy. We've looked at gravitational potential energy in terms of here on Earth, where we had the traditional MGH, all the way back in Unit 3, but what if we want to consider gravitational potential energy at any spot throughout the universe? So this requires a more universal definition, hence why we say universal gravitation, and we'll also be looking at how we can use gravitational potential energy in order to calculate a quantity of interest known as the escape velocity of an object. So defining gravitational potential energy. So recall again that the gravitational field produced near mass can be modeled as a curvature of what we call space-time, okay? So if we look at this curvature of space-time, the more dense, the more massive an object is, say like there's an asteroid, moon, and Earth, the more curved the space-time will be. So what this produces, if we think about as a spandex sheet, what we call a gravitational well, okay? So we can think of and analogize a gravitational field as what we call a gravitational well. The deeper the well is, the stronger our gravitational field for that object is on the surface of that object. Okay? So the depth of the well is proportional to the gravitational field strength G at the surface of that object. So asteroid has a tiny gravitational field at its surface, the moon has a stronger gravitational field, the Earth has a very strong gravitational field, and then so on and so forth. Alright? Because we can see the gravitational well gets deeper and deeper and deeper for each subsequent object. So gravitational potential energy. Gravitational potential energy is defined as the negative of the universal gravitational constant times the mass of our object producing a gravitational field times the mass of objects that are stuck in this gravitational field divided by the distance between the objects r. This equation right here seems quite similar to the equation for the force due to gravity, and that's because there's a connection between the force due to gravity and the gravitational potential energy, just as we saw with Unit 3. Except in the case of Unit 3, we're able to get the equation using algebra. In this case, getting the equation for gravitational potential energy would require what we call calculus. Okay? So the big thing you may notice here is that the gravitational potential energy is negative. Why is our gravitational potential energy negative? So the reason being is that the gravitational potential energy measures how bound two objects are in a field. So the gravitational potential energy measures the amount of energy stored between two objects in this gravitational field. So the gravitational potential energy measures how bound these two objects are. So as a result, if these two objects want to get separated and they want to escape each other's fields, they don't want to be bound anymore, a debt of energy must be paid in order to get out of the field. So a debt of energy keeps the objects trapped in the field, and so since we have a debt here, we associate that with a negative quantity of potential energy. Okay? So a negative potential energy always represents objects being bound in a system, meaning they're trapped in a system and thus have to pay a debt to get out. So at infinity, this potential energy goes to zero, since the debt that must be paid to not be bound in the gravitational field is zero if one is an infinite distance away from the other object. So if our guy is an infinite distance away from the Earth, they're not going to be in the gravitational field of the Earth. They're going to have escaped that gravitational field, so they don't have to pay anything to get out of the gravitational field. So as a result, the potential energy goes to zero at infinity because there's zero debt that must be paid. Okay? And for those of y'all who've had calculus, you can interpret this in terms of a limit, that the limit as r goes to positive infinity of our potential energy term is going to be zero because our potential energy is proportional to the inverse of our radius r between the two objects. So gravitational potential energy as a debt. Let's take a look at how weird this can be right here, okay? So Messier 87 is a black hole that was taken, that had a picture of it taken a couple years back, okay? Or at least a couple of years back at the recording of this video, okay? So if I calculate my potential energy at some distance r, or when I'm at the edge of Messier 87, I get my potential energy is negative 3.5 times 10 to the 18th joules, okay? While that seems like a large number, we have to recall this is actually a negative number, so it's actually really, really, really small. It's less than zero. So what this means is I'm trapped in the gravitational field of Messier 87, okay? If I am inside the black hole, this debt is going to grow now, okay? So it's my potential energy inside a black hole would be negative 4 times 10 to the 18th joules, okay? But my potential energy is actually decreasing because it's becoming a lesser number, okay? So this is really weird to think about, is that the debt grows, the amount of energy that I have to pay back grows in order to get out, but the potential energy is going to actually decrease because of the negative sign that is attached in front, okay? So in order to escape, I would have to pay 4 times 10 to the 18th joules to get out, which is more than if I was on the edge of the black hole, which would be 3.5 times 10 to the 18th joules. So the potential energy decreases. That means I have to pay more energy to get out, okay? So as a result, if my radius or my distance increases, meaning I'm escaping from the black hole, my potential energy is actually going to increase because I'm going to be increasing towards a potential energy of 0. Whereas if I move inside the black hole and my distance r decreases, my potential energy is decreasing because of this negative sign right here, okay? Meaning I'm becoming more trapped and my debt is getting larger and larger and larger. Conversely, what this means is that if I get closer to my if I get away from my black hole, the gravitational field strength is going to decrease because the gravitational field will have less influence on my motion. Whereas if I move closer to the black hole, meaning r decreases, my gravitational field will increase because I'm getting closer and closer to the center of the black hole. So as distance increases, potential energy increases, and the field strength decreases. And if distance decreases, my potential energy will decrease and my field strength will increase, okay? So a small little subtlety that you need to take into account right there, okay? So let's take a look at escape velocity, okay? So escape velocity is defined as the velocity that you must have at a certain point in space in order to in order to overcome the gravitational field at that point in space and escape from the gravitational field of your object, okay? So basically it means to escape the orbit. If you're in orbit around your object, it means, in layman's terms, to escape that orbit and to never come back, okay? So how do we determine escape velocity? So we recognize this is that the object must have an initial amount of kinetic energy that is at minimum equal to the initial amount of potential energy, all right? The idea being is if I'm moving at a certain speed in order to escape the gravitational field, that means there's an associated kinetic energy. This kinetic energy must be at minimum equal to the initial amount of potential energy because that potential energy is the debt that I have to pay. That means that my kinetic energy must be at least equal to that debt. So as a result, we're going to have our total initial kinetic energy is going to be equal to our initial potential energy plus our initial kinetic energy, all right? So that's at our initial point of interest. We're going to apply conservation energy here to determine our equation for our escape velocity, okay? So the final point of interest is going to be infinitely far away from the gravitational well, since we wish to be totally free of the well. Thus, the total final energy will be 0, as there's going to be no potential energy that we're bound to, and all kinetic energy is going to be used and paid back to the system to escape. So our final energy is going to be 0, okay? So that's the main concepts here, okay? So combining those main concepts then, we can derive a problem-solving process for determining escape velocity. We recognize that the initial kinetic energy is going to be used to overcome the gravitational potential energy, which means that the final energy will be equal to 0. So we set our initial energy equal to our final energy using conservation of energy, which gives us initial potential plus initial kinetic equals 0. So as a result, we're going to replace initial potential energy with the equation for potential energy, which is negative universal gravitational constant times the mass of the planet times the mass of our object divided by r plus 1/2 mv escape squared. So the equation for our initial kinetic energy that we need to have to escape. And this again is going to be set equal to 0. So now what we proceed to do is we solve the above equation for v escape. Okay? So we start off right here where we now are going to add our potential energy term to both sides since it's a negative, okay? Which is going to give us 1/2 v escape squared equals the gravitational constant times the mass of our object producing a gravitational field times the mass of our object that's orbiting the field divided by r. So the object that's orbiting the field that we want to escape the gravitational field, it has its mass appear on both sides of this equation. So just as with orbital speed, the mass of our satellite is going to cancel out, and we can see the mass of the satellite has no effect on the escape velocity. So we're going to get that the escape velocity squared is going to be equal to 2 times the gravitational constant times the mass of our planet producing gravitational field divided by the distance between the planet and the satellite. And taking the square root, we see that the escape velocity is equal to the square root of 2 times the gravitational constant times the mass of the object producing gravitational field divided by r. So again, we see right here for this equation that the escape velocity of our object that's in orbit around the planet does not depend on the mass little m of the object. The reason being is that the escape velocity depends on the underlying gravitational field strength, which, as we've discussed at this point, only depends on the mass of the planet producing the gravitational field and does not depend on the individual mass of the object that's orbiting. So the object that's orbiting is not going to have any effect on its own escape velocity, weirdly enough, just as we saw with orbital velocity. And if you notice, this equation is actually quite similar to the orbital velocity equation. It's actually the same equation as the orbital velocity equation. It's just multiplied by a factor of square root of 2. So if we have an object, and we'll see this in class, if we have an object that is orbiting a planet at a distance r, its escape velocity is going to be square root of 2 times its orbital velocity. And you can look at that comparing your notes, okay? So just as with orbital velocity, you need to be able to solve this from first principles, meaning from conservation of energy. So you need to be able to do each step in this problem-solving process right here to get your escape velocity, okay?